So Kp is an equilibrium constant, right? But rather than using concentrations, it's using what we call partial pressures. Because in reality, you very rarely measure. Yeah. Well, get it done and then we can get on with it. Okay. You don't normally measure the concentration of a gas in moles per dm cubed. You measure the gas's pressure, and the pressure gives you the idea of its concentration. Okay? So the P here stands for the partial pressure. So if you think about gases, you know, we are under the pressure of 1 atmosphere of gas now. There's 1 atmosphere of gas on us. That's what we feel all the time. And you think about, well, what gases are they actually on us, though? What are the gases around us? Nitrogen and oxygen, the main ones, aren't they? Yeah? Roughly, they're at 80% to 20%. So what you can say then is 80% of the atmospheric pressure pushing us is due to nitrogen, and 20% is due to oxygen. Yeah? The amount of pressure that a gas delivers is independent of what the gas is. It doesn't matter if it's N2, it doesn't matter about its molecular mass, or if it's double bonded or triple bonded. 1 mole of any gas occupies the same volume with temperature and pressure, or at any temperature. As long as the temperature and pressure stay the same, they occupy the same volume. So they will how much you have of them is proportional to how much pressure they exert. Okay. So if we want to know, rather than talking, we don't normally talk in percentage though. We talk about in what we call mole fraction. Okay, so the mole fraction is the number of moles of that particular gas divided by the total moles of all the gases. Yeah. So if we can work out the mole fraction of each gas and times it by the total pressure, we get the partial pressure of each gas. So partial pressure equals a mole fraction of the gas times by the total pressure. So basically, if you add up all the parts,
with oxygen, 0.2 times the total pressure.
Yeah, basically all the partial pressures have to add up to the total pressure. Yeah.
Oh, okay.
But the more you have of a particular gas in the mixture, the more it contributes to that total pressure. Okay. And it doesn't really matter what gas it is. It's irrelevant of what its molecular form.
So, like 0.2 times 1 plus 0.8 times 1 is equal to 1.
Yeah, exactly. Yeah. Okay.
Yeah. Okay.
So we can use these partial pressures instead of concentrations. Because we don't really it's not normal, it's not usual to work in concentrations when it comes to gases. We normally work in partial pressures. So if we have a look at this question, if you look at that's wrong one. What's it gone? Okay. We start off with the question. It's just about a rice question again. Okay. So first thing I want you to do is set out a rice. Don't do rice cake though, just rice. Don't worry about concentration. Just rice for this question. You know how much CH4 you start off with. You know how much water you start off with. Okay, you've got the ratio in the equation. It tells you how much CH4 there is at the end. Okay, so do a rice table for this particular one. Okay, so everyone's all right with ratio, yeah? Just take the balance numbers 1, 1, 3, 1, yeah? Initials from the question, isn't it? So it tells us we've got 1 mole of CH4, 1.4 moles of water, and then we assume then, doesn't mention anything else, we've got that's how they start off with those, the products, which makes sense, the products. Okay, so we've got 0 of those. And then it tells us that the mixture contains 0.2 of CH4. So we are 0.2. So just be careful that you put that in the right row. It's not gone down by 0.2, it's how much is left. 0.2. That's what you put in the mixture. So we do a quick sum there to see it's gone down by 0.8, can't we? Okay. So then we apply our ratio 1 to 1. So this will go down by 0.8 as well. This side, that side's gone down, so these sides are going to go up. So this one is 1 to 1 of those. This will go up by 0.8. This one will go up 3 times more. So 0.8 times 3 is 2.4. Yep. Okay. And then we just do the sums. So we've got 0.6, 2.4, 0.8. Okay. So this bit here is no different to case C. It's the next bit which is different, because when we work out KP, we do it in the same way, but we don't use concentrations, we use partial pressures. So KP for this reaction, you still have products on top. Okay, so you would have, but you don't put concentration, so you put the partial pressure of H2 cubed times by the partial pressure of CO, power 1, over the partial pressure of CH4 times by the partial pressure of H2O. Okay? They will mark you down if you did square brackets in that equation, because in this case, it's not concentration. Square brackets means concentration of. So, and here, that's not relevant. It's partial pressure of. But the method of doing it is exactly the same. Products on top, reactants on bottom, to the power of the balancing number. So we need to work out mole fraction, and then we need to work out partial pressures to put in there. So there's kind of like another 2 lines. Mole fraction, partial pressure. So these are all the moles that we have. We've got to work out what each one is of the total moles. So the first thing we need to know is what is the total moles. So we're going to plus these four numbers together to work out total moles. Is it?
1 plus 1 plus 3 plus 1.
Yeah. That's good. 4 moles. Okay, that's total moles. So then each one of these then to work out the mole fraction is what fraction is this out of 4. So we're going to divide each one by 4. So if you want to check you've done it right, the total mole fraction should always add up to 1. You can't add up to anything else. Yeah? It's all the fractions to make the whole. So the point of doing this is the fraction that each one of these gases contributes to the overall pressure inside that reaction vessel. Actually, you're right, look a bit lost. Sure. So if we look, they give us a total pressure, they tell us it's 30 atmospheres. Okay? Now, whatever they give you the pressure in, because pressure can have lots, it could have bars, can't it? It could have pascals, kilopascals. It doesn't matter, just stick to the unit they use and keep that unit. Yeah? Don't try and convert it because there's no point and you'll just get marked down because the conversion will always be, lead to some inaccuracies. So, to work out the partial pressure, the partial pressure is mole fraction of each gas times by the total pressure. So each one of these we're going to times by 30. Okay? That is okay. Times by 30, so that is the total pressure. Okay. So shout them out, what do you get? Huh? This is 3 over 2. Yeah. So 1.5, isn't it?
Yeah. Oh, you want numbers or fractions?
Numbers at this point.
Okay. That's 1.5.
Yeah.
And then 4.5. 18 and 6.
18 and 6. Okay, so it's 5, 6. Well, yeah, adds up to 30, doesn't it? Okay. The partial pressures should equal the total pressure. Okay. Again, you can check it out right. It doesn't, something comes wrong. Okay. Then you substitute those numbers into the top bit, don't you? So after all that hard work, make sure you put the right one in the right place. So we've got 18 cubes times by 6 times by 1.5 times by 4. The question they gave us, got 1, 2, 3, 4 significant figures. Well, 3 actually, if you look at the pressure. So 3 significant figures. Then what did you get for that?
5184.
5, 1, 8. Sorry.
5,184.
Oh, 5,000. So yeah.
184.
Okay, now we're going to need units again. Okay, now the units they gave us for total pressure were in atmospheres, so we're going to substitute atmospheres into here. So units for this kp, again it can be different for different kps. We've got atmospheres cubed times by atmospheres over atmospheres times by atmospheres. So we can go. Square? Oh, sorry, yeah. So that comes like that, yeah. So it's atmosphere squared. And the atmosphere is just one unit, so it's a bit easier. Okay, so it's basically Kc again, it's a little bit different at the end. And that's quite a big number. What would you say? What would you? Killer. So 5,000 is a big number. What does it mean? Okay. Well, that's good. I didn't understand the answer. If it's above 1, a number that's so 1 is like in the middle. If the position of equilibrium is about 1, it means that it doesn't really favour the left or right. So 5,000 says it really favours the right. Yeah. A really, really small number like 1 times 10 to the minus something really favours the left. So this reaction is very much going forward. It's a big number. Okay. There we go. Right. Okay. Let's get a little bit of practice on this then. If you turn to the very last page, please, of the pack I gave you, literally the back page, some KP questions there. Have a go at number 1, please. There you go. Literally the very back page of the large handout. Question 1, please. Yeah, you do those as fractions. Yeah, I think it's a fraction. It's going to be this fraction.
Done.
What's the name on the problem in the survey?
Oh, let's try to come on to that. So, let's just check how you. There it is. I'm going to hear your voice.
So 1A, what's the first thing you've got to do if we can work out, Amina, what's the first thing you've got to do if we can work out mole fraction, number 1? Yeah. So question number 1, what's the first thing you've got to do before you can work out mole fraction? Right, I'll have a look now. The question hasn't even got any harder. Question number 1, we've got to work out the mole fraction of each of these 3 gases. What would be the first thing you'd have to do? This one here, yeah? It says Kp at the top. Yeah, number 1, A. We want to work out mole fraction. What do we have to do first with all those moles of gases? Say again? So we want to know what fraction they are of the total. So the first thing we need to know is the total moles of gas, isn't it? Yeah, so we add those three together, 95 plus 55 plus 5. Does that make sense?
On the wrong page.
I think you are too. We're literally on the very last page of the booklet.
Oh, yeah, I have it.
That one,
On
yeah?
the wrong page.
Okay. So we add those up. So we've got 60, was it 155, yeah? And you divide each one of those by 155, and that'll give you the mole fraction. And then if you want to work out the partial pressure stuff, what would we do next? What would B? Yeah, so each one of those mole fractions you would have worked out, you times by 60. Okay, and that'll give you the partial pressure for each one. Okay, and then you work out Kp. Now, to see this Kp here, but everything in that reaction is a gas. That means it's a homogeneous equilibrium. Everything is in the same state. Okay, now, in a minute you'll see heterogeneous. Let me just show you on here. Okay. This is less common, but it can come up. This is what's on the boards there at the moment is a heterogeneous equilibrium. So you can see that there's two solids and a gas. It's a decomposition of calcium carbonate. But you can go backwards. Calcium oxide can absorb carbon dioxide. Now, if you think about a solid can't have a partial pressure. Okay, it can't have a concentration either because it's just constant. It doesn't change. So it becomes part of the equilibrium constant, part of Kp. It doesn't change. Yeah, because it's constant like that's a constant. So if you think what we would have had, products divided by reactants, we just don't have anything for those, we just have the products on top. So when you have an equilibrium which is heterogeneous, for Kp, you only include the ones that are gas. What would it be if the CO2 was on the other side, if it was a reactant? Yeah, good. 1 over the CO2 partial pressure. Okay? Because it's a product, it's over 1, which is, it's itself. Okay? So that's quite simple. Solids are emitted, they obviously have no pressure. Aqueous things don't have any pressure either, so they've been emitted. So heterogeneous, you only include the thing that you can actually measure the concentration of. In this case, Kp, that has to be a gas. Okay? Right, so if you look at number 2 then, this right